All right, guys, let's take a moment here, probably a lot of moments, and go through mini quiz number 2. We'll see how you guys did on this one. All right, so here are the answers to your 4 multiple choice questions, everybody. E, then A, then C, and then B. Let's go through them one by one and see how you guys did on this one. Okay, first question right here. We've got a horizontal line, y equals 2 here. That's an asymptote for the graph of the function, and then which of those statements must be true. So if we were looking to graph this, there's not really a whole lot that we can say about it for certain right now, other than the fact that at 2, we are pretty certain, we usually do asymptotes in red, so let's do that. We've got a horizontal asymptote cutting right through here, and that's really all we know for sure. So with that in mind here, the important thing right here is to notice that they're talking about which of the following statements has to be true. So if you guys remember back to geometry when you did some of those always, sometimes, never problems that people usually hated, this is actually kind of a good usage of that. All right, so the first one right there would be f of 0 is equal to 2, meaning that we've got a point right over here. One of the wrong impressions that people get about a horizontal asymptote, and this was true when you first learned about them back in Algebra 2 and again in pre-calc, is that a function can never cross its horizontal asymptote. What we now know is that a function can actually cross its horizontal asymptote. It would just need to do that typically at relatively small values of x. So for A, we've got something right here that very often is not true, but can be true. It certainly doesn't have to be true, though. So we know that A is not our answer for this one right here. How about for B? That our function, f of x, cannot equal 2 for all x here greater than or equal to 0. I did just notice that we're only talking about x is greater than or equal to 0, so I'm not sure that this left half of the graph here is relevant. This would be one for B here that I'm thinking a lot of people said here, that the function cannot equal 2 for all x greater than or equal to 0, but that is not the case. What we have right here, everybody, is really just a quick question right here about the definition of a horizontal asymptote, which I'll get to in just a second. So I would not be surprised if a lot of you said the answer was B. I'll check that when I grade that, but B is not going to be the answer. For C, f of 2 is undefined. That is completely irrelevant to this problem here. F of 2 is the y value of the function at this particular spot right over here. 2 is an x value in C. We're talking about a y value of 2, so C is definitely not the answer. Okay, if we take a look at D, the limit as x approaches 2 of f of x is equal to infinity. What they are talking about right here in D is the presence of a vertical asymptote. A vertical asymptote is what happens as x is approaching a finite value, but its limit is infinite or negative infinity there. And again, in D, that certainly could be the case, but it does not have to be the case. The correct answer here for number 1, everybody, is E. And the reason why is because the absolute very definition of a horizontal asymptote that we wrote down way back when we covered this in chapter, oh boy, I want to say we were doing limits, it was in chapter 2, is that a function has a horizontal asymptote if the limit as x approaches either positive or negative infinity of f of x is equal to a particular value then that we're going to call c, a finite value. If that happens, then y equals c is a horizontal asymptote of that function. So E, it was a really easy answer to come up with if you knew the definition right here of a horizontal asymptote. Remember that we saw some weird graphs over the years, guys, or over the year, I should say, of functions that can actually cross their horizontal asymptotes, but then kind of do something like that as they move on. So, all right, E is the answer to number 1. I wouldn't be surprised if a lot of you had B. All right, let's move on to question number 2 right here. The derivative g prime, I bet that's important right there, not g, but g prime of a function g, is continuous, has exactly 2 zeros. Now that is important right there because in a lot of problems out there, everybody, you're given zeros within a table, but those aren't necessarily the only spots. But here they tell us that this function here, g prime, has exactly 2 zeros. So since we're given both of them, we know where they are, at x equals -2 and at x equals +2. Okay, keep reading here. Selected values of g prime are given in the table above. If the domain of g is the set of all real numbers, then g is decreasing on which of those intervals? Okay, so they want to know about the behavior of g, but we're given information about g prime. So what we should remember, guys, is that g decreases on an interval here where g prime is negative. Inversely, we know that g is going to increase on any interval here in which g prime is going to be positive. So what we know right here, everybody, is that our derivative here, g prime, is only equal to 0 twice, once right here at -2 and once right here at +2. That means then that everything to the left of -2, and here they've given you -4 and -3, but anything that went further than that, the derivative of g is always going to have the same sign. And here we see that those values of g prime are positive. That means that on this interval right here, for everything less than -2, we know that g is increasing. There's no chance that, like, I don't know, at -10, the derivative could suddenly turn negative again, because they told us that we had exactly 2 zeros right here. There can't be any more, and there would need to be another one in order for this to have a change in behavior. Okay, in between these two x values of -2 and 2, we can take a look right here and realize that g prime is negative, which means that g has to be decreasing on that interval. And for everything greater than 2 over here, we can see that our g prime values are always going to be positive, which means that g has to be increasing. So the question was here, g is decreasing on which of the following intervals? The only spot that it can be decreasing is on this interval right here, in between -2 and +2. So it looks like our answer for number 2 is going to be A. Moving on to number 3. This was a calculator question, and I see a whole bunch of irrational decimal answers right here, which means I am probably going to have to go through here and use my calculator in order to figure this out, but let's see what we have going on. A particle is moving along the x-axis so that its velocity is given to us by this function right over here, and they want to know the acceleration of the particle. Okay, what we hopefully remember from back in chapter 3, section 4, I believe, when we were doing PVA problems, is that the definition of your acceleration function, it's going to be the derivative of your velocity function, everybody, v prime of t. And this isn't that hard of a function to come up with the derivative by hand right here. So let's run with it, although I should probably show you guys a refresher on how to do this on the calculator right here. So the derivative of your velocity function, well, the derivative of that 3 is just going to be 0. We've got 4.1 times the cosine of an angle. Derivative of cosine is negative sine of the same angle, so that is going to get us a negative of 4.1 multiplied by the sine of the same angle, which is a 0.9t, but then multiplied by the derivative of that angle, which is a 0.9. So I'm going to cram that right in front of that 4.1. And we can simplify this if we were so inclined right here, but I'm not really sure that it's relevant here. They asked what's the acceleration of the particle at 4, so now I think we can go ahead and evaluate a of 4, and there's really no harm in just typing this into the calculator the way it's written. So let me switch over here and see if I can do this with you guys. So we have, here we go, a negative 0.9 multiplied by a 4.1 times, let's see, that was the sine, negative 0.9 times a 4.1 sine of 0.9t. But that t value we wanted to put in here was 4. So we're going to put all that together right there and get a 1.6329. I got to change a setting on that. Rounded to 3 decimal places, guys. 1.633 should be the answer that we get there. So a 1.633 gives us an answer here of C. Certainly wasn't difficult to do the problem that way, but actually this step that we took right here, everybody, was kind of an unnecessary risk. Remember that your calculator will evaluate a derivative for you at a particular spot. So let's see if I can remember how to do this or figure out how to do it on the iPad. For you guys, you would hit the menu button, and when I hit that little wrench right there, we get to the same thing. And if we go to the calculus menu and ask it to evaluate the derivative at a point, what's going on right here? Our variable, technically we were doing t here and not x, so there we go. We'll change that to a t, although we certainly could put an x in there. The value, we wanted to evaluate this when t was equal to 4. And yeah, we were looking for the first derivative, that's right. So we wanted to do the derivative with respect to t of the function that they gave us here, which was, if I recall, a 4.1, nope, 3 plus 4.1 cosine of 0.9t. All right, so here we go. So a 3 plus a 4.1 times the cosine of a 0.9, and then our t variable right there, and evaluate all that when t was 4. That should get us the exact same answer there, and it did. Oh good, I have a Pokemon notification. This is what happens when you steal your kid's iPad. Anyway, yeah, we got the exact same value right there. The benefit to doing it that second way, I didn't have to actually compute the derivative of the function at all. I could see that being a spot where somebody made a mistake. Maybe they forgot the chain rule or something like that. In fact, if we were to take, let's see what would have happened. If we had forgotten the chain rule, I could get that answer just by dividing by the negative 0.9, which we had to put out in front. I'd be willing to guess that that negative 1.814 is one of the wrong choices right here. Oh no, it was just the positive one. Oh, I shouldn't have divided by the negative. I see why that's the case. That negative would have been there regardless. So anyway, D would have been a fairly common wrong answer, I would have thought, in this problem right here, but the correct answer is C. Okay, moving on to number 4 right here. Sounds like a volume problem. Base of a solid is a region in the first quadrant. All right, so let's draw something going on right here. A first quadrant region bounded by the y-axis. The graph of y equals the inverse tangent of x. Okay, hopefully we remember, everybody, that the graph of tangent of x is going to look something like this. So the graph of the inverse tangent is just going to get flipped over the line y equals x, and is going to look something like this, and it does that in the third quadrant, although I don't think we care about that because we're just talking about a region in the first quadrant. Okay, so we are bounded by the y-axis, that graph, the horizontal line y equals 3. What is probably worth talking about right here is the idea, in fact I just erased it, but let's go back to it. If we were to draw the graph of tangent of x, which looks something like this, people seem to remember fairly well that tangent is unique among your trigonometric functions, at least out of the 3 basics, in that it has vertical asymptotes, and that first vertical asymptote is right there at pi over 2. Now, when we take the inverse of that to graph y is equal to the inverse tangent of x, that vertical asymptote of pi over 2 now becomes a horizontal asymptote. Okay, so that line right there is y equals pi over 2. Now I bring that up because they told us that the horizontal line y equals 3 was a boundary of this region. Pi over 2 roughly is about 1.5, so if I had to worry about when y is equal to 3, I'd go ahead and draw that horizontal line right over there. So that's interesting. And then also the vertical line x is equal to 1. So let me go ahead and just kind of randomly, I'm looking at the scale of the 3 there, put a 1 right about there and see if we can't figure out what's going on. I didn't use the y-axis there in blue. So we're looking here and here. All right, everybody. So with those 4 boundaries, let's see what we had and make sure we have it all right. There's the y-axis. There's the graph of y equals inverse tangent of x. The horizontal line y equals 3. And the vertical line x equals 1. Okay, we got it, guys. That, almost like a trapezoid, except it's curved on that one leg there, that's the region that we're talking about. Okay. So that yellow region right there becomes the base of a solid. And what we're doing here is we're drawing cross-sections perpendicular to the x-axis, and each of those cross-sections becomes the base of a square. So we're going to draw a vertical piece right over here, everybody, kind of looking something like that. And that piece in red that we just drew becomes the side of a square, so I'm going to label that as S. What I hope you guys can see from this graph right here is that S is going to be a variable quantity whose value is going to depend on where we are here in terms of x. So we should probably take a moment right here and write s as a variable expression, top minus bottom. Well, no matter where we draw s, it's stopped by y equals 3 on top, and then underneath it, it's bordered on the bottom by y is equal to the inverse tangent of x. Okay, not real pretty, guys, but that's about the best that we can do for S. All right, from that one piece right there, we're now going to draw a square kind of sticking up here. That was really badly drawn. We're going to draw a square sticking up. So what do we remember here, guys? That the area of a square is simply equal to its side length squared. And since the side length is what we just came up with right here, we're going to rewrite that as 3 minus the inverse tangent of x quantity squared. And in some cases, it's worthwhile to try to simplify that expression, but in this one, nothing really happens right there. So that is as good as we're going to be able to make our cross-sectional area function. And from there then, everybody, let's see what we can do to clean this thing up now. They wanted the volume of the solid. Well, if you guys recall, every volume problem we ever did used the exact same formula, and here we go. Volume of our three-dimensional solids was always equal to a definite integral of your a of x function. And that a of x function is what we just came up with right there, the 3 minus the inverse tangent of x quantity squared. We're integrating this with respect to x because everything was perpendicular to the x-axis. And the only thing we're missing here are the limits of integration, which need to be the lowest and highest values of x in this region right here. Well, pretty clearly we can see that that lower limit is going to be 0, and the highest x value we're going to need is 1. And since this is a calculator question, and again I can tell because of all the crazy decimals in the answers right there, we can go straight to the calculator and try to type this whole thing in. So let's see what this one looks like. All right, again guys, I'm going to go to menu and we're going to do an integral. Integral starting at 0 and then going up to 1. Got it. And then our integrand in parentheses, let's see what we had there. 3 minus an inverse tangent of x, quantity squared. So 3 minus, how do I do inverse on here, guys? What if I held down tangent? Yeah, there it is. So 3 minus an inverse tangent of x. Close the ratio. Close the binomial right there, and we want to square all of that. And we're integrating all of this with respect to x, and that should do it, everybody. So let's hit enter, and I got a 6.612 for that answer here. So let's jot that down, 6.612, and sure enough, that looks like one of the answers, which is B, and yep, that was the correct one. Okay, and moving on to the free response question right here, everybody. I believe that this one was given to you as a non-calculator question. I didn't include that right here, but I'm pretty sure that's right. Okay, so what's going on right here? We are dealing with the graph of f, everybody, 3 line segments, so we don't have to assume what looks obvious, which is that it's piecewise and linear. Okay, and what do we have here in part A? Let g be the function given by this integral right here. G is a definite integral of f of t starting right here at -4 and then moving to the right from that, it looks like. Okay, and for each of g of -1, g prime of -1, and g double prime of -1, find the value or state that it doesn't exist. Okay, so let's get working on this one. Probably better take a moment and rewrite that expression right here. So for A, we were just told that g of x is a definite integral starting at -4 and going up to x of the function f of t taken with respect to t. Let me double check that and make sure I've got that right. We do. And then we want g of -1 for starters. This is probably the most direct of the 3 questions. Not the easiest, but the most direct one. They gave us the definition for g of x, so everywhere there was an x, we just replaced that with a -1. So it's an integral from -4 to -1 of the graph of f of t, which they gave us, taken with respect to t. So this is basically an area problem. As we look at this region right here, starting at -4, which is right here, and ending at -1, they just want to know what is the net or signed area of that region right over there. Okay, well, it looks like a trapezoid, everybody. So the area of that trapezoid is going to be a 1/2 times its height, which is actually running horizontally right here, which is going to be 3 times the sum of its bases. And it looks like we have a 3 on the left and a 2 on the right. So a 3 plus 2 is going to go right there. That is a 5 times a 3, which is 15, and half of that is going to be 7.5. Now let's talk about the sign of that answer. Two things you need to think of. Number one, and pretty clearly, this region is located entirely below the x-axis, which implies that it's going to have a negative value for the integral. The only kicker would be that if your limits of integration were in the wrong order, with the larger value on the bottom as the lower limit and the smaller value up on top as the upper limit, that would flip around your answer. But that did not happen in this case. Those numbers were in the proper order, and so for that reason here, our answer is going to be negative 7.5. Okay, that's the first part of this one. The second part, I think, is actually going to be the quickest and easiest one to answer right here. They want to know the value of g prime of negative 1. Okay, well, the important thing to take from this right here, and you've seen me do this maybe from time to time, but let's do it again right here. We've got a concept right over here that's pretty important, that g is equal to an integral, or if you will, an antiderivative of f. So basically, that tells us that little g is equal to capital F, the antiderivative of little f. If we were to now just go down the ladder right here and differentiate this equation on both sides, we end up with this really simple concept. G prime is equal to, and we denote the derivative of capital F as little f. And the last part then, if we do it one more time, if we take the derivative of each of these here, we're going to get that G double prime is exactly the same thing as f prime. This is a little table, if you will, a little explanation of the relationship at all three levels here that I write down in almost every one of these problems. So as we go back to example A, what we're looking for now is g prime of negative 1. And this second row of that table tells me that g prime of negative 1 is going to be exactly the same thing as f of negative 1. Because g prime is the same function as f. And f of negative 1 is simply going to come from reading the table right here, and of course I crossed it out, but there you go. F of negative 1 had a y value then of negative 2. So that is the answer to the second part. And let's switch to green right here. And the last thing they wanted was g double prime of negative 1. Okay, going back to the little table right over here, g double prime is the same as f prime. So g double prime of negative 1 is equal to f prime of negative 1. Still not a hard question to answer, but we got to think about it a little bit more right here. F prime of negative 1 would be the slope of the tangent to this graph of f right here at the spot where x is equal to negative 1. Well, unfortunately, what we have at this spot right here is kind of this unnatural connection between two different linear parts of this function. What we have right there, guys, quite simply is a corner, and that tells us, guys, at a corner that the derivative of a function is undefined. So I hate it when people write equals undefined because that doesn't make any sense, but we'll just write that f prime of negative 1 is undefined. And they did lay that out for us as a possibility then, everybody, back in the directions right there, or state that it does not exist. Actually, that's probably what I should have written right there. So f prime of negative 1 does not exist. And I would like to think that if you guys got a little bit lazy and wrote DNE, they would understand what you meant, but not quite sure about that. So anyway, okay, that takes care of part A. All right, guys, let's take a look at what's going on in part B. Let's go back to the original problem to do that. B says, for the function g that was defined in part A, we're going to find the x-coordinate of each point of inflection of the graph of g. Okay, so a point of inflection in the graph of g comes from where its second derivative changes sign. Well, we've already talked about the idea that the second derivative of g is the same thing as the first derivative of f. So if we want to know where the second derivative of g changes sign, that would be the same place as where the first derivative of f changes sign. And notice here in B, they talk about explaining your reasoning. So I'm actually going to begin with that. That's the way I always prefer to do these problems. So what do we want to know here, guys? Where does g have a point of inflection? So I would probably start off by saying that g has a point of inflection at a spot where g double prime of x, oh boy, there g double prime of x changes sign. from positive to negative or from or vice versa. But at the same spot, and again, don't misinterpret the word or, this is really meaning just another way of writing it, where g prime of x changes sign, or where f prime of x changes sign as well, because f prime and g double prime are the same thing, or where f prime of x changes sign. And f prime of x changes sign at a spot right here where f of x, the function itself, changes behavior, either from increasing to decreasing or from decreasing to increasing. And I think we can tell that, everybody, by looking at the graph. So we can say that this occurs at, all right, guys, and we're looking for a change in behavior of the graph of f. The function was increasing, it's still increasing, but then at the end now it starts decreasing. This spot right here, everybody, is the only spot on this graph right here from -4 to 3 where f changes behavior. So this occurs only at x equals 1. I'll even add the word only right there, and that should be it. Let me go back and read the question again. Find the x-coordinate of each point of inflection. There we go, and explain your reasoning. I think we've got that one. Okay, let's take a look at part C, everybody, and see how we're proceeding here. All right, let h be a function defined by, and this is something new that we haven't seen before, so I'm going to write that down. Integral from x to 3 of f of t. Okay, so h of x is a definite integral. They don't usually give it to you with a variable on the bottom, but that's exactly what they did here. So I think we're going to have to watch out. That wasn't right. I think we're going to have to watch out then for the idea that our limits of integration might very well be in the wrong order. Okay, so an integral from x to 3 f of t dt. Find all values of x in the closed interval for which h of x is equal to 0. Okay, so we want to know when this function right here, h of x, is equal to 0. And we were doing that on the interval here, I believe we said from -4 to 3. Okay, well, one answer should be jumping out at you right away. If x was equal to 3, then right away we see that property there with the same limit being used twice. And it doesn't matter what function you're integrating then. If it's the same limit top and bottom, you know that value is definitely 0. So x equals 3 is the quick and easy answer that we were able to come up with. So I hopefully snuck a point in right there. Even if we didn't do any other work right there. All right. Hi, Megan. How you doing? All right, let me get rid of all of this junk here. Oh, you know what? Actually, I'm going to do this. Okay, and we said that x equals 3 was one of our answers. But we're also interested in anywhere else on this graph here that the net or signed area between the curve f of t and the x-axis was going to equal 0. So I feel like we better go back right here and see what else we can do to clean this up a little bit. And unfortunately, I made a big mess right here, so let's see how much of this I can kind of get rid of. Oh, no, not that. All right. Maybe I can just move some of this. No, man. I'm wrecking it all. Okay, you go away. No, you stay where you were. You go. I give up. All right, anyway, this is the graph that we're looking at right here, and we want to know anywhere else that an integral here that was starting at 3, that's important right there, guys, an integral that was starting at 3 and ending somewhere, and it would have to be to the left here, was going to equal 0. Okay, so if we begin this graph right here and kind of work from right to left, I'm hoping we can see that the first spot I see something like this happening is right here at 1. At that spot, we've got a triangular region above and a congruent triangular region below. So that integral here from 1 to 3, or backwards from 3 to 1, that one's going to equal 0 as well. And because we're trying to get this to equal 0, it doesn't matter actually what order we're doing it in. So that's going to happen again at x equals 1. Okay, and let's keep trying to read this backwards. So we're kind of starting over again right here. As we move a little bit more to the left from there, I've got this skinny triangular region above, and again, if I get to right here, there's a congruent skinny triangular region that's below. So at this spot here, since the two blue triangles cancel out and these two red triangles cancel out as well, we've got another spot right here at -1 where the value of this integral is going to equal 0 as well. And I'm pretty sure that's the last one, guys, because if we go any further to the left, we're simply taking area here that is underneath the x-axis, and we're never canceling that out with any area that's above the x-axis. So those three should be our sole answers for C. It did not say anything about justifying or explaining, so even though we just kind of talked our way through that, that should be good enough to get full credit here for part C. And then what's going on right here in part D, everybody? All right. For the function h defined in part C, find all intervals on which h is decreasing. And there it is again, guys, to explain your reasoning. So again, I like to begin with the explanation. All right, so we wanted to know where on this interval right here that h was decreasing. All right, so for D, everybody, we can say that h decreases where the derivative of h prime, which, by the way, would be equal to, and hang on, let's go back to where we were just a second ago, and let's do this same little trick we tried earlier. H is equal to an antiderivative of little f. So h is capital F. Differentiating both sides, h prime is little f, and h double prime is going to be f prime. So if we want to know, everybody, where h is decreasing, we want to know where h prime, which is the same thing as f, is negative, where h prime equals f is negative. Okay, and we can say here now that this occurs on an interval here. Now we're looking for anywhere that this graph f is negative. Oh boy, it was negative right here, and it was negative until it got to here. So we're on an interval here starting at -4 and ending at 0. It goes positive for a while until it gets to 2, and then it jumps to negative again. Okay, so it looks like we have one interval here from -4 to 0, and another one then from 2 to 3. So on an interval here from -4 to 0, it's tempting to put the word and here, but we really should put the word or, an interval here going from, nope, not that, an interval here from 2 to 3. And that should take care of that. All right, just a quick check of our answers here, guys, to make sure that we got everything correct. Does that work? Sorry, guys, learning as we go. Okay, so our answer for A was -7.5, -2, and then it does not exist. There's our -7.5 right there. There's our -2, and there's our does not exist. Okay, so that's good. For B, we said our only point of inflection was at x equals 1, and for B, there we go, x was equal to 1. Gotcha, because of the change in behavior, so that was good. For part C, we came up with 3 answers here of 3, 1, and -1. Their answers right here, yep, 3, 1, and -1, gotcha. And for D, we said that h was decreasing on an interval here from -4 to 0, and again from 2 to 3, and got a problem with that one right there. H is decreasing, they said, only on the interval from 0 to 2. What did we do wrong on that one here, guys? Let's take a look at that one. H is decreasing where h prime was going to be negative. All right, so how do we get that one wrong? All right, so we had, now hang on just a second right here. I think I see the mistake that we made right here. When we went ahead and did this one, yep, okay. I thought that was going to be an issue, and then I forgot all about it. The fact that those limits right there were backwards means that we probably should have rewritten this right here as h of x is equal to, would have been the opposite of an integral from 3 on the bottom to x on the top of f of t dt. And what that meant, everybody, is that when I went and differentiated that right there, h prime actually would have given us the opposite of f. I needed these limits in that order right there in order to apply fundamental theorem of calculus part 2. So that was my mistake in looking through that. H prime should have been the opposite of f, and h double prime should have been the opposite of f prime. So what that means then, everybody, is we were looking at a spot right here for h prime in order to be negative. We actually wanted to know where f itself was positive. Okay, so that was my mistake then, guys. So I was looking for intervals on which this graph of f was negative, but what we really wanted, oh, I'm running out of colors here, was just the spot where this graph was positive. So that was only going to occur right here, and that is from 0 to 2. All right. So basically, what should we have said right here? H prime decreases where H prime, which is equal to the opposite of F, is negative. And I tell you what, if I had to do all this over again, which I do, let's get rid of that. Okay, where H prime, which is the opposite of F, is negative, I'll just keep going in purple right here. Or, let's put it this way, where H prime, now let's just do this, where F is positive. There we go. And now we can say that this occurs on the exact opposite of what I had before, everybody, which was the interval here from 0 to 2. And that should match the answer that they had on that one right there. Okay, yep, my mistake there, guys. Okay, so if you took a look at all of the scoring standards right here in all of these options, sorry, I went through that kind of quickly. So for part A, get a score based on some of that here. Part B, I'll go through and grade based on these as well. Those are the point values there for part C. And lastly, for part D, located right over here, we're going to be using the exact same scoring rubric for every one of these problems that we do. So when you guys get a score returned to you on Classroom, it's going to be based off of this rubric right here. Okay, guys, hopefully we did okay on that one. We're going to do another one next week, and we are going to count that one for a grade.